Next, we will discuss another very common pattern that it will be very beneficial if you learn to recognize, just like the geometric and the telescoping series. So let's consider the series that look like this. And this is what we will call the p-series. So for example, this is the p-series. And how do we know? Because if I replace p in the pattern above with number 2, I will get exactly this example. Now, we also know that radicals can be expressed in an exponential form, and therefore this is also a p-series, but p is equal to 1/2. And something a little bit more complicated will look something like this. This is also p series, and p in this case is equal to 2/3. Now, the well-known harmonic series is actually also p series with p equals to 1. And the question now is, how do we know whether a given p-series converges or not? So this is the question. Does this series converge or does this series diverge? And what we're going to do is we're going to consider the following function, and we are going to check whether this function satisfies the following 3 conditions. Is this function continuous? Yes. Is this function always positive? Yes, because if we only have positive values of x, then there is no reason for this function to ever be less than 0. And finally, is this function decreasing? If you graph this function, you'll see that regardless of the p-value, this function will be always decreasing as long as x is positive. And what does this mean? That means that we can set up the integral test, and according to the integral test, this series behaves exactly the same way as this integral, but this integral behaves differently depending on the value of p. If p is greater than 1, then this integral can be done with a simple, I guess, just with the simple power rule, and it can be easily shown that it converges when p is greater than 1. However, when p is less than 1, it can be shown that this integral diverges. And when p is 1, it also can be shown that it diverges. This is the case for the harmonic series. So the same now applies to the p-series. And this is what we will be calling the p-series test. Basically, it says the p-series converges if p is greater than 1, and the p-series diverges if p is less than 1, just like that. So immediately we can analyze the following series, or the convergence of the following series. Does this converge or diverge? Well, we recognize this as p-series, with p being equal to 5. And since 5 is greater than 1, we conclude that this series converges by the p-series test. So let me just print the conclusion down here. And we're done, just like that. Here's another example. Does this series converge or diverge? Again, we recognize this as p-series, with p equals to 1/4, which is less than or equal to 1, and therefore this series diverges by the p-series test. And that being said, p-series becomes now one of the types that we do want to recognize as soon as possible. So we're going to adjust our strategy for analyzing the convergence of some series that we developed earlier. So if you have a question about the convergence or divergence of a series, the first thing we want to do is we want to recognize whether it is geometric or telescoping. And if you remember, then we would set up the divergence test. If it was neither one of this, we would set up the divergence test by setting up the limit and checking whether it is equal to 0 or not equal to 0. If it's not equal to 0, then we are done. And if it is equal to 0, then we continue to step 3, in which we would run one or several convergence tests. And one of the tests that we learned already was the integral test. And now we learned the p-test, but the p-test is such that we would want to recognize the p-series as soon as possible. So we're going to add the p-series to our first step of the analysis, meaning we would want to recognize it as soon as possible. Why? Because it is a very simple test, and you really don't want to miss out on it. So we went over the p-series test